Hi all. So in the last class we have discussed the propagation of transverse wave in a rod. So today we are going to discuss the longitudinal wave. So I think you already familiar with this distinction of wave, that is transverse and longitudinal. The transverse means the propagation of wave and the oscillation are mutually perpendicular. So this transverse nature we have already discussed. So this kind of wave. So if you consider a stretch string and oscillation, if it is perpendicular to the propagation, then it is called transverse wave. Then what is longitudinal wave? The longitudinal wave would produce if the oscillation is parallel to the direction of propagation. So when we can produce, how we can produce longitudinal waves in rod. So we already discussed how to produce transverse wave in a stretched string. The transverse wave can be produced by oscillating the free end of a stretched string. So how we can produce a longitudinal wave in a rod? So one of the simple example to produce a longitudinal wave in a rod is to take a rod and just strike it using a hammer. So if we strike it using a hammer, then the sound would produced. This sound would obviously propagate through this rod, and this propagation of this sound is basically due to the oscillation of particle inside this rod, and this particle would oscillate parallel to the direction of propagation. So therefore, this is an example of longitudinal wave. Okay, so how we can discuss or how we can explain this longitudinal wave, or how we can find out the expression for the speed of the wave in case of the longitudinal waves in a rod. So for it, we can have this figure. So let us, this is our rod, this blue color is a rod. And what we'll do is we'll consider the different planes in this rod. So suppose this red color shaded region represent a single plane, and B color, this green color shaded region, it is another plane. So this A and B are two equilibrium plane. A and B are two equilibrium positions of two planes. And when the wave propagates, what would happen is this plane would oscillate. So this red color double-sided arrow represent the oscillation of plane A, and green color the shaded arrow, the green color double-sided arrow represent the oscillation of plane B. Okay, so this both the plane A and B oscillates, and its oscillation would be in the direction of propagation of wave. So this would be the direction of propagation of wave. Suppose this is the direction of propagation of wave propagation. Okay, so this A and B are the two equilibrium position, and A prime B prime are the displaced positions. A prime and B prime are displaced positions. So then we represent delta x is separation between A and B, and when it oscillates, the separation may change. So this delta x plus delta y may be the separation at during its oscillation. Okay, so then what would be the change in separation due to the oscillation? The change in separation between the planes due to oscillation, that would be equal to the percent separation, which is delta x plus delta y, minus the initial separation, which is delta x, and that we can represent as delta y. Okay, so then it is easy to define the longitudinal strain the longitudinal strain is defined as the change in separation divided by the original separation, delta y divided by delta x. That would give the longitudinal strain of these planes. Okay, so then it is very easy to find the stress on plane A. Okay, so usually the stress is defined as the modulus of elasticity. So since it is the rod, we can define Young's modulus in the strain. So that would be equal to Young's modulus can be capital Y times delta Y by delta X. So for delta X tend to 0, stress would be equal to Y times dy by dx. Okay, then what would be the force on A? The force on A would be stress into area. So since capital A is already represented for the plane, so we can represent the small a is the area of the plane. Then stress is y dy by dx times A. So this would be the force on the area A. Then what would be the force on B? The force on B would be the force on A. We can represent by symbol FA, FB, the force on A plus df by dx times delta x. So this is equal to y a dy by dx plus y a d square y by dx square times delta x. So therefore the net force, so that can be FB minus FA. The net force would be equal to FB minus FA. This y a dy by dx would cancel. That would be equal to y small a d square y by dx square times delta x. Now according to the Newton's second law, net force is equal to mass into acceleration. Okay, so we cannot use small a here. So net force is equal to mass into acceleration. Okay, now what is the mass of the segment between A and B? That would be equal to density into the volume. So density into the cross-sectional area into delta x. And acceleration can be written as d square y by dt square. Okay, now these two, equation number 1, equation number 2, the right side can be equated because the left side is net force. And therefore y a d square y by dx square delta x is equal to rho a delta x d square y by dt square. Now this delta x cancels, a cancels, and therefore d square y by dx square is equal to rho divided by y d square y by dt square. Now this is nothing but a differential equation of wave, and it is called the wave equation. Remember, a general wave equation is, so better we can represent the partial derivatives. Dou square y by dou x square is equal to 1 by v square dou square y by dou t square. So this implies that this represent this equation, the equation number 3 represent the wave equation, and the 1 by v square equal to rho by y, or the speed of wave would be equal to square root of y by rho. The speed of longitudinal wave in a rod is given by square root of y by rho. So not that the speed of the wave is independent on the dimension of the rod. It depends only on the Young's modulus, that is the modulus of elasticity, and as well as the density. It inversely proportional to the square root of density. So when density increases, the speed decreases, whereas the elasticity increases, the speed increases. So the velocity of longitudinal wave in a rod depends only on Young's modulus and density of rod. Okay, so next we'll discuss the same thing in case of gases. So better we can continue the same discussion.